All right, this is the second PowerPoint for Unit 1. We left off talking about empirical formulas, and we're going to start into the structure of the atom. Atomic model of the atom states that the electron, instead of being in one particular orbit in one place, it is actually more like a cloud instead of an individual spot. So it's compared more to a spinning airplane propeller. So in that general region is where you might find an electron, not that exact spot. It determines the allowed energies that an electron can have, and how likely you are to find the electron in a particular place around the nucleus. So it's not that things are in a definite orbit, but it's more of a probability of where you're going to find the electron. So the different kinds of orbitals that we can have. Remember, we can have s orbitals, and we're not going to, y'all talked about this before, so we're not going to delve into where they originate from, but you can have s orbitals. You can have p orbitals, and those p orbitals can exist on all three axes. And then we can have 5 d orbitals that exist, and then the last one are the f orbitals, and there are 7 different variations of an f orbital. Orbital diagram, we always start at the bottom with the lowest energy at the bottom, and we work our way up, okay? I recommend that you go back in the PowerPoint that is posted in Schoology and watch this video just to kind of get a review of where these quantum numbers come from and why there's 3 P's and 5 D's and 7 F's. So that'll just be a little review video for you. All right, so let's delve into electron configurations. So let's start with hydrogen, the easiest element. We have 1 electron in hydrogen because it has an atomic number of 1. So we put it in the first or the lowest energy level. And that would be the first energy level, 1s, 1. The subscript tells the number of electrons. The letter tells the type of the orbital or the subshell. And the number tells the electron or the energy level. Okay, so electron configurations can be done 4 ways. You can do the straight electron configuration, just like we did. We can have an orbital notation diagram, which uses the boxes with the arrows indicating the opposite spins and how many electrons are in each orbital that way. We can do a noble gas configuration, which means we go back to the last filled noble gas, and then we add everything else after that. A valence electron notation is just where we put in the S and P electrons. Those are our valence electrons, or the highest energy level electrons are our valence electrons. You remember that the periodic table also helps us to determine what the electron configuration should be, or the order of filling the electron configuration. We start with a 1s up here at hydrogen. And we go across, so that's 1s1, 1s2, and then we come down. Here's our second energy level. We fill the S's and the P's. Third energy level, S's and P's. Fourth energy level, things get a little weird because we start using the transition elements in here. So those are where we're actually filling the d orbital, okay, and which actually slips in a little bit above the 4s. And then we start filling the 4 d's. Now, the 4 S's are the valence electrons. They have a higher energy than the D's. Okay, so we'll remove those electrons. Well, we'll get to that later. Okay. So here are some examples of orbital diagrams and electron configurations for some of our elements. Let's just pick carbon. Okay, carbon has 6 electrons. It has an atomic number of 6. So we put 2 in the first, which is 1s2. We put 2 in the second, which is 2s2. And then we start filling the P. So that's 4. We have 2 more electrons to put in. So we have to put in 1 electron in each p orbital before we start pairing them. So that's why we have these electrons looking like this. They're not paired up. There's 1 in each. And then For nitrogen, we put in the third one. You see they're all unpaired right now. And then it's not until we get past nitrogen that we start filling up and pairing those electrons in the p orbital. Okay. Here's some electron configuration practice problems. So again, we just look where these are on the periodic table. That's atomic number 19, means it has 19 electrons. We start at the bottom and we fill them until we run out of electrons. So 1s2, 2s2, 2p6, that gives me 10. Here's 18, and one more makes 19. Okay. Orbital diagrams, same. I do the same thing. I just write it differently. So instead of writing the subscript, I'm going to write the 2 arrows for the 2 electrons. So, oops. So I'm going to put in my 2 electrons in the 1s, then the 2s, the 2p, the 3s, the 3p, and this would be my last valence electron here, the 4s1. So electron configuration, orbital notation, they're the same thing, it's just 2 different ways of writing it. On this one, we're looking at electron configurations of ions. So remember, if we have a negative charge, that means we added 2 electrons. So oxygen normally has 8. If we add 2, that gives us 10. 10 electrons goes in, again, start at the bottom, 1s2, 2s2, 2p6. Okay. With a positive charge, remember we are subtracting an electron, or we're taking an electron away. So that means instead of 11 electrons, it now has 10 electrons. Again, same configuration because it's 1s2, 2s2, 2p6. Start at the bottom, work your way up till you run out of electrons. The transition metals, things get a little funny with those, again, because that d orbital is a little bit, it's kind of on the same level as the 4s orbital. So what you need to remember is that the d sublevel is not the valence electrons. It's the 4s that is the valence electron. So when we start pulling off electrons, they're going to come off the 4s first, then the 3d, and then, yeah. So they'll come off the 4s and the p first, and then they'll come off the 3d. Okay. So for iron with positive 3 charge, that means it has 3 less electrons. So that means I'm going to start taking them off the 4s2. So I'm going to pull them out of there first. And then that third one is going to come off of the 3d. And that gives us this configuration down here. 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, because I removed that 4s orbital. Here's another example, and I do need to make sure that you make one correction. At least on the PowerPoint, this needs to be corrected. That is the incorrect notation for molybdenum. It is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d4. And that's very easy to do because you can just go back and look at the periodic table and just follow across in the periodic table until you get to the element molybdenum. If I were to remove 5 electrons from that, again, those electrons are going to come from the 5s. So those are going to be taken first. And then 3 of the 3ds are going to be, 4ds are going to be taken, and that's only going to leave me with 1. Noble gas configurations, again, we just go back on the periodic table, we go back. So from phosphorus, we go backwards to neon, and then whatever's left over, we write after that. You can play that video in the PowerPoint. It's just a little extra review for noble gas configurations. Isoelectronics. Isoelectronics are where we have different elements, different ions, but they all have the same configuration because they all have the same number of electrons, okay? So in each of these cases, these are all 10 electrons. If we add 2 electrons to oxygen, that gives me 10. If I add 1 electron to fluorine, that gives me 10. If I take, neon just normally has 10, neutral neon does. If I take 1 electron away from sodium, that gives me 10. And if I take 2 away from magnesium, that gives me 10. 10 electrons is always 1s2, 2s2, 2p6. All right, spectroscopy. Spectroscopy is just where we are taking that knowledge we have of electron configuration and using it to help us identify different compounds and elements. Mass spectroscopy is where we separate things, separate atoms based on their mass, on their size. So it's a magnetic kind of field. So the heavier ions will come off at a different time than the lighter ions. So they get separated based on their mass. And from that, we can determine what elements are in a particular compound. Okay, so there's our picture. How many isotopes are represented by this spectrum? Which element does the spectrum represent? Calculate the average atomic mass. Okay, so what we do is we look at the size of these peaks will help us determine how many electrons are there and what orbitals the electrons are in. And once we figure that out, then we can use that to find out what element this particular element is. So we can see that it's falling right between 6 and 7. So what elements have a charge to mass ratio of about 6 or 7, or an atomic mass of around 6 or 7? We know lithium, if we look on the periodic table, lithium is 6.94. Okay, so we know that this element must be lithium, but there are different kinds of lithium. There's lithium with a charge to mass ratio of 7, and there's lithium with a charge to mass ratio of 6. And so we take the average of those two together, and that's where we get the 6.94 from. Okay. All right, let's look at another example. So in natural lithium, 7% of the lithium has a atomic mass of 6, and 93% almost has an atomic mass of 7. So when we average those two together, we get the atomic mass of lithium. It's a weighted average. So we multiply the atomic mass by the percentage in each case, and then we divide by 100. Another way you could think of it is you could go ahead and change those to decimals first. And then add them together. And that's going to give us our average of 6.941. Okay, another type of spectroscopy that we have is called PES, and this is photoelectron spectroscopy. And what it does is instead of using a magnet and based on mass, it uses high energy X-rays to knock electrons off of the atom. And we use this data to support electron configurations. So from this type of spectroscopy, the PES, we can determine the electron configuration of a particular element and then and its ionization energies, and then that'll help us to identify what element it is. All right, so here's an example of a PES data. This is what the spectrum will look like. So we can see that we have 2 electrons here. So this is the relative number of electrons. So we can see that this peak is twice as big as this peak. Okay, so And the size or the energy here lets us know which ones are at the higher level. So this one that is twice as high that needs to be the second main energy level, or it is our valence electron. So I'm sorry, I said that backwards. I'm sorry. The highest energy is going to be our lowest energy level, because those are the hardest ones to knock off. So these electrons, they are being knocked off. The hardest ones to knock off are the ones closest to the nucleus. So that has to be our 1s2, and it's twice as high, so 2 electrons, compared to this one, which was knocked off very easily and only has half the height. So that is a 1s2, a 2s1. The element with that configuration is lithium. Let's look at another example. Okay, so here we have several different ones, but it's still the same concept. So this is our energy from 0 to 10, from 10 to 100, 150. So this is the one closest to the nucleus, and then this one be the one furthest away. So this one has a relative height of 1, and this is 2, and this is 6. So these are s orbitals, and these are p orbitals. Okay, so this one is going to be our 1s2. Okay, then this one needs to be our 2s2, our 2p6, our 3s2, our 3p6, and our 4s1. So that configuration is representative of the element potassium. It's being slow. Okay. There you go. All right, so again, I look and I see where's my highest energy. Now, be careful looking at the energy. It's not always going to go from lowest to highest, so make sure you look at the numbers. So we see in this case, this is the highest one, okay? And then we go from there, okay? So I think this is the same slide filled in. Here we go. All right, so this is that slide we just saw. Because this is the highest energy, it has to be the 1s2. Then here, this has to be the 2s2. You can notice this one is 3 times bigger. So 2 times 3 is 6. So that is our 2p6. And here's our 3s2, our 3p6. And notice this one here is half the size of this one. That means instead of being a 4s2, it is a 4s1. Okay, so that's what we do with these. We just look at the relative heights. All right, and that is it for electron configuration, the structure of the atom, and spectroscopy. We will do a third video looking at periodic trends. So if you have any questions, and it's a lot of material, if you have any questions, let me know, and we'll see you in class. Have a great afternoon.